Hello everyone, myself Dr. Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to today's presentation on Sampling Distribution Part 4. Overview of today's presentation. Today we are going to solve some problems on the sampling distribution when sigma is known. In the previous session also we have solved some problems on the same, and I would like to continue the same today also. Now problem number 3. Determine the mean and standard deviation of sampling distribution of means of 300 random samples, each of size n equal to 36, are drawn from a population of size 1000, which is normally distributed with mean 22.4 and standard deviation of 0.048 if sampling is done with replacement and without replacement. So here we need to solve the problem in two different cases. One is with replacement and the other is without replacement. Also find the finite population correction factor. Now first, the given data. It is given that total number of samples is equal to 300. Next, and size of each sample, size of the sample, which is denoted by small n equal to 36, drawn from a population of size 1000. So size of the population, capital N equal to 1000, which is normally distributed with mean. So the mean of the population is also given in the problem, mu equal to 22.4, and standard deviation of the population, sigma, is also given 0.048. Now the question is to determine the mean and standard deviation of sampling distribution of means. So we know that in sampling distribution of means, first one, with replacement. So with replacement means the sampling with replacement can be considered as sampling from an infinite population. So in the case of infinite population, this mu x bar is equal to mu and sigma x bar equal to sigma by root n. So what is the mean given in the problem? 22.4. So mu x bar is 22.4, and what is mu x bar? The mean of sampling distribution of means, which is the required one in first case with replacement. Next, the standard deviation is sigma by root n. Sigma is 0.048 divided by root n 36. So which results as 0.048 by 6, which is 0.008. So in the first case with replacement, both the mean and standard deviations are obtained. So for that reason, we have to consider these standard results. In the case of infinite population, that means with replacement, mu x bar is mu and sigma x bar is sigma by root n. Similarly, second case without replacement. Without replacement means an element of the population cannot be selected more than once from the population as it is not replaced back. So in without replacement, this is finite case. In this case, the mean of sampling distribution of means is again the same, the actual population mean, and the sigma x bar is sigma by root n into under root capital N minus small n by capital N minus 1. So what are the given values? Mu is 22.4. So this value is 22.4. Then sigma is 0.048 under root divided by under root 36 and capital N, the size of the population is given as 1000 minus 36 by 1000 minus 1. So, this is 0.048 by 6 multiplied by root. So, this is 964 by 999, and this value is calculated in the previous case. In the case of infinite population, it is 0.008. So, 008 into this value, and using calculator you can find this final result as 0.00790,605. This is the standard deviation of sampling distribution of means when the population is finite or the sampling is done without replacement. So, like this, using these conditions, properties, we can find the required values, mean and standard deviation. And also it is required to find the finite population correction factor. What is this finite population correction factor? Capital N minus small n by capital N minus 1. So, which is 1000 minus 36 by 1000 minus 1, which results as 0.97665. So, the finite population correction factor is the term under this square root, and this comes under finite case. So, capital N minus small n by capital N minus 1 is 0.97665. So, this is the finite population correction factor. Now, coming to the next problem, determine the expected number of random samples having their means between 22.39 and 22.41, greater than 22.42, less than 22.37 for the problem 3. So, for the previous problem, that means we consider the same data given in the problem 3. And for that problem, we need to calculate the expected number of random samples having their means between these two values and greater than this and less than this value. So, to find the number of random samples, first we need to calculate the probability of a sample that whose mean lies between these two values. Similarly, to find the number of random samples having the mean greater than 22.42, first we need to find the probability of a sample which has the mean greater than 22.42. Similarly, the last one. So, here again we need to consider the same data, the number of samples, total number of samples given in the previous problem 300, and also the population mean mu 22.4 and population standard deviation 0.048 and we have the standardized sample mean, standardized sample mean. The formula is Z is x bar minus mu by sigma by root n. This is the standardized sample mean. That means the sample mean x bar is transformed into Z, which is called the standardized sample mean. So, here in the first problem, x1 bar is 22.39 and x2 bar is 22.41. Let us consider these two values. And we have the formula for Z is x bar minus mu by sigma by root n, and x bar will replace by these values, and mu is 22.4 by sigma 0.048 by root 36. So, this is Z value, and if x1 bar is 22.39, then Z1 equal to, let us substitute 22.39 here, 22.39 minus 22.4. So, it gives a negative value, whereas in the case of Z2, 22.41 minus 22.4, so which gives a positive value. And what is the difference here? 22.39 minus 22.4 and 22.41 minus 22.4, the 0.1 difference. So, we will get the corresponding negative and positive values. So, simply substitute these two x1 bar and x2 bar here, so that we can obtain z1 and z2, and the values are given by minus 1.26 and the values are given by z1 equal to minus 1.26 and z2 equal to plus 1.26. And in the first problem, we need to find probability of x1 bar lies between 22.39, 22.41, which is same as z lies between minus 1.26 less than z less than 1.26. So, negative to positive, integral from minus 1.26 to 1.26 f of z dz. So, this is equal to, between negative and positive values, there will be 0. And if you draw the standard normal curve, and this is minus 1.26, let us consider, and here 1.26. So, we need to calculate this region, and here we have 0. Since the curve is symmetric about this y-axis, the normal curve is symmetric about y-axis. So, it is symmetric about f of z. So, the negative portion is equal to corresponding positive portion. The negative portion is equal to corresponding positive portion. Therefore, this minus 1.26 to 1.26 can be calculated using 2 times of 0 to 1.26 f of z dz, and this value can be obtained using the standard normal table 0 to 1.26 given by 0.3962 and multiplied by 2, that gives 0.7924. But what is this value? The probability of a sample mean lies between 22.39 and 22.41. But the question is to find the expected number of random samples. So, we have total number of samples is 300. So, therefore, the expected number of samples whose mean lies between 22.39 and 22.41 is equal to 0.7924 multiplied by 300, which is equal to 238. So, in 238 samples, the sample mean lies between these two values. Similarly, the second problem greater than 22.42. So, the second one, x3 bar is 22.42. Now, if x3 bar is 22.42, what is z3? So, use the same formula, 22.42 minus 22.4 divided by sigma is 0.048 by root 36. So, this results as 2.53. So, therefore, we need to calculate x bar greater than 22.42, which is same as z greater than 2.53. So, again draw the graph. 2.53 is a positive value. So, I can consider here, and this is the region we need to calculate the probability or the area under the normal curve. So, this is z and f of z 0. We need to calculate this region, but using the standard normal distribution table, we can find the area from 0 to any z value. Hence, we know that this total area is equal to 0.5. So, from this 0.5, if we subtract this region, we will get the remaining shaded region. So, this is 2.53 to infinity f of z dz, which is 0 to infinity minus 0 to 2.53. So, that is equal to 0 to infinity, this f of z dz will be 0.5 minus 0 to 2.53, that we can calculate this region using the standard normal distribution table. So, the value is given by 0.4943, and hence the final answer is 0.00057, where the probability is very, very low. And here we need to calculate the total number of samples, the number of samples. Therefore, the number of samples is given by 0.00057 multiplied by 300. So, which results as 1.71, and since these are number of samples must be an integer, so we can consider as 2 samples. So, in 2 samples the sample mean will be greater than 22.42. Similarly, the third question, less than 22.37. Less than 22.37, and again if x4 bar is 22.37, what is the value of Z? So, 22.37 minus 22.4 by 0.048 by root 36, which results as minus 3.8. So, a negative value for Z. So, therefore, we need to calculate x bar less than 22.37, which is same as Z less than minus 3.8. Z less than minus 3.8 means minus infinity to minus 3.8 f of Z dz. So, if you draw the graph and denote the point negative value, this is Z 0, f of Z, negative value somewhere here minus 3.8. We need to calculate this shaded region. And we know that this total half region is equal to 0.5, and from that if we subtract the area from minus 3.8 to 0, that gives the remaining shaded region. Therefore, if we subtract the area from minus 3.8 to 0 from 0.5, we will get this shaded region, and therefore, this value is equal to minus infinity to 0 f of Z dz minus 3.8 to 0 f of Z dz. So, this is 0.5, and we know that the negative portion is equal to corresponding positive portion since the curve is symmetric. This is equal to 0 to 3.8 f of Z dz, and we can find this region using the standard normal distribution table. And the area from 0 to 3.8 is given by 0.4999, and the final result is again very low probability 0.0001. And this is the probability that random sample can have the mean less than 22.37. But we need to calculate the number of samples. Number of samples is equal to this probability multiplied by total number of samples, 300. So, almost we can consider as 0. There is no sample whose mean is less than 22.37. So, like this we can find the required probabilities or the number of samples using the sampling distribution of means when sigma is known. In today's session, we have solved some problems on sampling distribution of means when sigma is known. In the next session, we will discuss the sampling distribution of proportions, sampling distribution of sums, and sampling distribution of differences. So, we consider two populations with mean mu1 and mu2, standard deviations sigma 1 and sigma 2. Then if we consider the difference between these two, mu1 minus mu2, and if we consider sum mu1 plus mu2. So, we discuss sampling distribution of proportions, sums and differences in the next session. This is for today's session, and we will meet in the next session. Thank you.